Hello, thank you for joining today's webinar on developing electric machines to meet durability and reliability targets. So I'm Jonathan, and I'll start the presentation today. So to begin with, we can just do a bit of a recap of the webinar series so far. So we began with a kind of looking at the vehicle model and the overall ambitions and objectives for this series. We moved on to concept design optimization, detailed electromagnetics with Maxwell and Motorcad, thermal simulation, ANSYS Fluent, and so now today we're looking at it a bit closer at sort of durability and mechanical stress, in particular for the rotating system of the electric machine. So a bit of an overview of the agenda. So we'll start with a bit of a recap of the initial specification and sort of the base design that we came to following the optimization strategy we saw in the second webinar. Brilliant. So as a reminder, sort of the design of electric machines is quite a multi-physics endeavor. There had sort of quite a few different requirements covering electromagnetics, thermal, mechanical, and electrical. So today, so one of those parameters that we looked at during the optimization procedure was on the rotor mechanical stress. So this was a test done at a kind of overspeed condition, what was set to 20% over the nominal maximum working speed. And this, we set a kind of limit based on the kind of material being used, the sort of yield stress of the material. Took some averages in certain regions of the geometry, and used those as a kind of requirement that the machine sort of had to meet, alongside other requirements for things such as torque, power, and thermal performance as well. And a bit of a reminder, a bit of a kind of what that was. So this is for the what ended up being the optimized design, the final design that was sort of created through the optimization. And so you can see here the geometry in the bottom left. We've applied sort of automatic rounding to the templates, the template geometry. It was varied in the optimization, but we've taken averages of stresses in some key regions, which you can see sort of being the magnet post, which is the kind of central area between the two magnets, and another area that's kind of close to the air gap, which we're calling the bridge. So these two areas are kind of where we kind of see quite high stresses. It's a multi-physics problem because electromagnetically, and want them to be as small as possible to minimize flux leakage. However, there's a minimum strength that we need to maintain for working at high speeds. And a bit of an overview analysis. So this is a linear FEA analysis in Motorcad, ANSYS Motorcad. It's kind of very fast, so it can be done as part of an optimization. It's parameterized the geometry as we vary. And we're applying some kind of simple techniques. So moving the magnets to the top surface, so there's a contact, filling with air, and having a kind of setting an adhesion factor. So initially starting with a factor of 1, so we're using the kind of nominal sort of Young's modulus for the magnet. And you can see here the values in the bottom right that we got from the optimization and from this kind of optimized design. So this kind of is the starting point for the kind of workflow that we're going to go through today. So I'll hand over to Henry next. So on to
Thanks,
Henry.
Jonathan. Yeah, thanks, Jonathan. So for detailed analysis in mechanical, the goal is first, we want to verify and also optimize the setting in Motorcad and have good correlation between linear mechanical and Motorcad simulation. Second goal is that we want to kind of have more detailed design around the magnet pocket in mechanical and doing a nonlinear analysis to have a full, more physical simulation and get more accurate results. And third goal is we want to do some type of optimization and find a structurally minimum stress based on the parameters we choose. So to do this kind of study, first we import geometry, do some type of meshing settings to refine the mesh, and then we compared two types of contacts, linear versus nonlinear, and apply boundary conditions and look at different factors to affect the results. So in terms of geometry, first we can export geometry from AutoCAD, either use DXF format. If you use that option here, as we showed in the upper right side, you can select the DXF format and bring into Discovery and simply choose select all the edges and fill it. That will create a surface geometry for 2D plane stress analysis in mechanical. Or you can simply export this AutoCAD design and save as a Python code, and then you can import the Python code, run the script directly in Discovery without any manual intervention. So that's a probably easier way to import geometry. After the geometry imported, you can do some mesh refinement study. Typically, we command some type of convergence study. The picture shown on the left has a mesh with sorry, switch back slide here. The mesh to the left is the baseline mesh we started with. It has about 90,000 nodes, and after a couple iterations, we find the mesh onto the right, which has about 230,000 nodes, give us stress results that's less than 5% difference compared to the previous mesh iterations. So the stress results around the magnet pocket, it is sensitive to the mesh setting, so we strongly recommend to do this type of refinement study. We also recommend using inflation layer settings around the pocket to capture the stress accurately, as we showed in the settings here. In terms of mechanical setup, typically we do this type of analysis using plane stress stage, and we typically submit only one single sector is the full 360 simulation to speed up the model. Typically, to simulate this kind of cyclic symmetry boundary conditions, we use a CPCYC command as we showed here, and you can see the more details in the documentation to simulate this kind of symmetry. Or if you're in the design iteration stage, you can simply approximate as a friction support, which is more rigid, but give you a similar results before the final validation stage. In terms of mechanical setup, what we try to apply here is a rotation velocity, which applies 20% over maximum speed, which is 18,000 RPM here. And in the model we showed in this simulation using linear bounded contact, we apply friction support on the edges of two edges here. For the first model, we applied the linear bounded contact between the magnet and the rotor lamination. We simply bonded the magnets with the edges, outer edges here, because we know due to centrifugal force, the contact really happens between in this region, and here shouldn't be any much tension or bonded contact at all. So here are the results from the linear analysis in mechanical. We can see higher stress around the bridge, layer 1, layer 2, and also the post. We see similar, if we compare with the result from AutoCAD, we see similar results around those area, and we see slightly lower stress in AutoCAD. And the next, we did a sensitivity study. What we're trying to find is what kind of parameter are sensitive to, what kind of parameters settings in AutoCAD affect the stress results. And from this sensitivity study from Optislam combined with the Optislam, what we found is the mesh density affects the mesh density around the rotor void settings here affects the stress the most. And other mesh settings also have smaller impact, which also emphasize we need to have a fine enough mesh to capture the stress concentration. And what we found also the adhesion factor, which basically scales the modulus of the magnets to simulate this kind of soft contact effect due to epoxy, does not affect the bridge, the stress around the bridge. It affects most around the stress around the magnet post. So here's a recommended setting for the MotorCAD to give the similar results as we showed here. As we see, if you see this plot, the maximum stress is now is closer to the mechanical simulation, and here it has the difference, mostly within 5% difference between the linear mechanical simulation as well as the MotorCAD simulations. Next, what we want to do is instead of this kind of raw pocket shape design from the MotorCAD export, we want to add some type of more detailed retaining feature to constrain the magnet more properly without using bonded contact, because that's more physical, and it's also one of the goals for the structural design. With this kind of retaining feature, we don't use linear bonded contact anymore. We can use more physical nonlinear friction contact. And because of nonlinear friction contact I use, it's more challenging to have a converged solution. So we suggest you can use scale the normal stiffness factor as well as the stabilization damping factor that can help you convert the model and solve the model in a more reasonable amount of time. So here shows the results from nonlinear model with friction contact between the magnet and the rotor lamination. And here is the original model using linear bonded contact between magnets. We can see the stress in the nonlinear contact model is 13% less compared to the linear bonded model, which makes sense because the bonded contact typically tend to be too stiff and lead to higher stress concentration around the along the bridge area. Here, a zoom-in view between the two models. There are two different geometry, two different simulation strategy. One is bonded, one is nonlinear contact. We can see the pattern of the bridge area are similar, but not exactly the same. So to capture the stress around the bridge, especially if we look at fatigue, we look at the peak stress, it's important to have such a nonlinear contact and detailed retaining feature properly modeled in mechanical. Here shows the displacement results of the outer edge of the rotor. We can see that both very similar, less than 1% difference between linear bonded and nonlinear models. How about the effect of epoxy? Some users asking us to include the effect of epoxy. So here we showed one model. We fill the gap here with the different material and assign the material property as the epoxy. The material property here are used from MotorCAD material database. Due to the epoxy, the very thin layer between the magnet and the rotor lamination, we need to use very fine mesh to capture such details, which lead to a larger model and a longer simulation time. And when we look at the results,